Hello everyone. On this video we will be covering the extrema of functions for two variables. Okay, so to kind of explain what we're doing, I want you to consider 3 points on a 3D plane, and those 3 points are enclosed in a region that we'll call R. Excuse me. Okay, so if we draw that out, in our 3D plane, X, Y, and Z. Okay. Let's say that first, actually let me make that a little bit bigger. So we don't have to squeeze everything in one little small region. Okay, so we have our X, our Y, excuse me, and our Z. Okay, so let's say that our surface is some three-dimensional blob that will look like this. Okay, so some three-dimensional blob just floating in space, in our 3D space. Okay, so let's say if this is our value of x equals a, and this is our value of x equals b, and this is our point AB on our xy plane. Okay, let me move this up a little bit. There we go. So it's not interfering with the A. Let's say this is some value that we'll call X. And this is some value that we will call Y. And let's say our X and Y is right here. Okay, so now let's say we have our value X equals some value C and Y equals some value D. Now let's say that C and D meets up to about there. Okay, so that's our point C and D. So we have 3 points on our 3D plane, and those 3 points are enclosed, let's say, inside of this square. It could be a square, it could be a circle, it could be anything at all. But inside this region here, we'll call that region R. Okay, the entire shaded area that has all of our points in it. Okay, so let's say for AB, that goes up to our f of AB right there. Okay, so that's our f of AB. Okay, so xy, let's say our xy goes up to about here. That's our f of xy. So that should be pointing to that. And let's say our CD, let's say that goes up, probably should have moved it over a little bit. That goes up to our highest point there, so that's our f of CD. Okay, Okay, so we have our f of xb, f of xy is right there, and our f of cd is there. Okay, so in this case, move my paper up a little bit, we see that our f of ab is actually less than or equal to our f of xy, which is less than or equal to our f of cd. Okay, now if this is the case, let's say if we let f be defined on an enclosed bounded region that we will call R, which is exactly what we did there. Okay, we could say that f of AB is the minimum of the function, f of xy, well, we say f, if our f at the point AB is less than or equal to our f of x, y. But that's for every xy point in that region. Okay, so if you pick every xy in this region, that will be the smallest. Okay. Okay. This is your absolute minimum. Okay. Now, on the other hand, let's say your point, our function at CD, that would be the maximum of the function f. That's only if our function at the point CD is greater than any other or equal to any other function at xy. And that's for every xy in the region. Okay, and that's your absolute maximum value. All right, so that's kind of a quick overview as to the idea behind the absolute minimum and maximum. Okay, so if you are still writing, feel free to press pause, but we're going to give out the actual theorem. Put the paper down. All right, so that leads us to our extreme value theorem. Okay, so we're going to let our f be a continuous function of two variables x and y. Okay, and they're defined, of course, in our closed bounded region. That we will call R in the xy plane. Make sure that's cleared up. Okay, so for our extreme value theorem, we know that One, that there's at least one point in that region that's a minimum value. Where F takes on a minimum value. Two, there's at least one point where F takes on a maximum value. Okay. Now, there's a difference between what we call an absolute minimum or absolute maximum and a relative minimum and maximum. Okay, so far we've been talking about the absolute maximum. That means the highest point overall or the lowest point overall. Now we're going to look at the difference between, and I'm just going to write that as, I know that's by the way, but that's between for me. I'm just shortcutting it. Absolute minimum or maximum values and relative. Okay. Now in some texts they'll call the relative minimum and maximum the local minimum or maximum. Okay. Where the minimum and maximum, of course, they just clump those together as the extrema. So you see the extrema, they just mean the minimum and maximum and or maximum. Okay, so you go right into the definition of the relative, or in some cases it's called the local extrema. Okay, now one, the function that we will call f, that would be considered the local minimum if that's the lowest point in an open disk. So as long as it's the lowest point around that point. So the function f is a relative or local. I'll write that a few times so you can make sure you understand that those two mean the same thing. Minimum at x0, y0 if f of xy is greater than or equal to f of x0, y0 for all xy in an open disk containing x0, y0. Okay. Now the local maximum, the function f is a relative or local maximum at x0, y0 if f of xy is less than or equal to f of x0, y0 for all xy in an open disk. Oh, move that up some. containing x0, y0. Okay, so really all this means is that the point x0, y0, z0, here I'm going to write that out for you. Let me move that to the next page. So if you're still writing, feel free to press pause, but we're going to explain this kind of in simpler terms on the next page. Uh-oh. There we go. All right, so really all that means is that, in other words, the point x0, y0, z0 is either the highest point or lowest point of all nearby points. Okay. Or in other words, all of the points in its neighborhood. Remember that from a few videos back when we talked about the neighborhood. Okay? So the difference is there can only be one absolute minimum and maximum, but there could be several local minimum and maximum. Okay, that's what's the difference between the two. So there could be several relative or local, remember they're the same thing, minimum or maximum values. Oh, I'll say maximum points instead of values. It's a little more precise. Okay, but only one absolute minimum or maximum. I guess you could say values. And values could work, because we're looking more at the value of z. Okay, so in order to find those minimum and maximum values, we have to know how to find the critical point. Okay, so if we look at the definition of a critical point, oh, that could be capitalized too. Doesn't have to be, but I think I'll capitalize it to show its importance. Okay. Now the critical point here is pretty similar to the critical point when you were looking at the first derivatives in Calc 1. It's not a whole lot of difference to it. Okay, this just applies to 3 dimensions instead of 2. Okay, so what if we let f be defined on an open region, remember our open region is R, containing x0, y0. Okay, so then the point x0, y0 is a critical point if either, okay, now this is the important part for the critical point, 1 partial with respect to x at x0, y0 equals 0, and partial with respect to y at x0, y0 equals 0 both exist. Okay, remember that's both of them has to exist. That's a key point there. So sometimes you'll have one exist and not the other. Or 2, our partial with respect to x at x0, y0, or partial with respect to y at x0, y0 does not exist. Okay? So if either doesn't exist, they're a critical point at x0, y0, or whatever value of partial with respect to x and partial with respect to y equals 0. Both of those would give you your critical points. All right. So in other words, one way you could say this is that if f has a relative, which also is the local, extremum at the point x0, y0, on an open region that we call R, then your x0, y0 is a critical point of f. Okay. Now, how do we know that whether the critical point is a minimum or maximum? We'll actually use what we call the second partials test. Second partials test will show if the critical point is a minimum or maximum. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go over these second partials test. There we go. Okay. Second partials test. Okay, so what if we let f have continuous second partial derivatives? Continuous, keyword. Continuous second partial derivatives. On an open region. And that region, we'll just call that R. Containing the points A and B, where partial with respect to x at that point A and B equals 0, and the partial with respect to y at the point A and B equals 0. Okay, so those things all have to be applied before we're going to apply the second partials test. Okay, so as long as those conditions are met, our test for relative, or in other words, local extrema of our function f So the first thing you want to do, solve the equation. D is equal to the second derivative with respect to x at the point AB times the second derivative with respect to y at the point AB minus partial with respect to x then y at the point AB squared. Okay. Now, once you solve for that equation, 1, if D is positive, so if D is greater than 0, and that's the key right there, f of second derivative with respect to x at AB is greater than 0, or second with respect to y, AB is greater than 0, then our function f has a relative minimum at our point AB. Remember, that can also be our local minimum at AB, or relative minimum. Okay? Now, 2, again, let's say our value of D is greater than 0, and our second derivative of x at our point AB is less than 0, or our second derivative at y is less than 0. Okay, it could be either or. Then our function f has a relative maximum at AB. Again, that could be also called the local maximum. All right. So what if you solve for D and D comes out to be negative? Okay. So if you look here, in order for D to be positive, both of these would have to be positive. Second derivative with respect to x and y would have to be positive. This is already going to be negative. If you have minus a negative number, that's going to be negative. So as long as these are both positive, you should come out with a positive number in most cases. But if you happen to have that D is less than 0, then the point A, B, and F at the point AB is what we call a saddle point. And at a saddle point, it's neither local minimum or local maximum. I'll put the little parentheses there. Which is neither local minimum or local maximum. All right, so to kind of give you an idea of what a saddle point looks like, basically because it looks like a saddle, I'm going to attempt to draw a saddle, at least the graph, the mathematical graph of what we call a saddle. More than likely, you might want to look up your textbook because my drawing is not going to be that great. Just warning you ahead of time. So if you look at your textbook, you'll see a more precise drawing of a saddle. Okay, so let's say if you have say there, and say better yet, bring that down just a little bit. There we go. Okay, so if you have, let's say, try to bring it out a little bit. Okay, so that's kind of how a saddle looks. Hopefully you can draw it better than I can, but your point where it kind of leads into the saddle, if you notice that it's you can't say it's the minimum because you have minimum values. You can't say it's the maximum because you have values that are bigger. It kind of sits right in that, and you can say, I guess you could say an abyss, where it's neither a minimum or a maximum. Okay, like I said, you will see a much better picture of a saddle in your textbook, so I would recommend doing that first. All right. Okay, and 4, let's say if you solve all of that and you end up with d equals 0. Then the test is inconclusive. Okay, which means you just have to figure out the minimum and maximum another way, or either the minimum and maximum may not even exist. Okay, it just means that you can't use this particular test for it. All right. Now, quick note, if you don't want to try and remember that formula, you can use the second determinant for the 2x2 determinant to remember the formula. There you go. Okay, so remember the 2x2, so d is equal to second with respect to x, second with respect to xy, second with respect to yx, and second with respect to y. Okay, so you have f of x times f of y minus f of xy times f of yx. Remember, it's continuous, so xy is equal to yx. So partial with respect to x, y squared. Okay, that's just a little shortcut to remember the formula. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and jump into our examples. All right, so let's say, for example, let's say if we want to find the local extrema for, say, f of x, y is equal to x squared plus y squared plus 2x minus 6y plus 6. Okay, so to do that, we're going to have to find our first derivative with respect to x, our first derivative with respect to y, our second derivative with respect to x, our second derivative with respect to y, and our derivative with respect to x and y. Okay, so we're going to have to find all of those. Okay, so you find our partial with respect to x. That's going to give us 2x. That will be a constant, so that's 0 plus 2. Constant, constant, so those will be zeros. And give a little bit of space. Our partial with respect to y is going to equal, that would be a constant, so that disappears. That would be 2y minus 6, because those two will disappear. Okay, so we have our partials with respect to x and y. Now we have to find out where those will equal 0. So partial with x equals 0, and our partial with y equals 0. Okay, so that's just 2x plus 2 equals 0. So we see that x is just equal to 1. And this is just 2y minus 6 equals 0, which shows that y is equal to 3. Okay, so we see here that that should be negative 1. Negative 1, 3 equals our critical point. Okay, so once you find your critical point, find your second derivatives. Okay, so your second derivative with respect to x is 2x plus 2. You're going to take that with respect to x again, which ends up just being 2. Our second derivative with respect to y, that's just 2y minus 6. You're going to take that with respect to y again, which is just going to end up being 2. Now our partial with respect to x, then y, that's just our partial with respect to x, and that with respect to y. So we're going to take 2x plus 2 with respect to y. Okay, since that's with respect to y, and y should be a little smaller. There we go. You take this with respect to y, that's considered just one big constant, so that's going to be 0. Okay, so we have everything we need here. Okay, so at the critical point, negative 1, 3, our d is equal to, remember that's the second derivative with respect to x at our critical point, so that's negative 1, 3, times our second derivative with respect to y at negative 1, 3, minus our partial with respect to x then y at negative 1, 3 squared. Okay, so we can see here that we have no variables here. So our second derivative with respect to x at negative 1, 3 is just 2. So that's going to be 2. Our second derivative with respect to y at that point is again just 2. So 2 times 2 minus our partial with respect to xy at that point is still going to be 0. So it's just 0 squared. Okay, so we know that is equal to 4. Okay, so we see here that d is equal to 4, which of course is greater than 0. Okay, so we take into consideration that our second with respect to x is greater than 0 and d is greater than 0. We know that our first, or our conditions for number 1, are satisfied. Okay, let me go back to the previous sheet. Uh-oh. Sorry about that. I keep having to remember to bring that up. Okay, so we kind of go back to the previous sheet of paper real quick. We see that the number 1, d is greater than 0, and our point there is greater than 0. So we know that it's a relative minimum at AB. Okay, so we know where A, B, F of A, B is a local minimum. Okay, so that means that our -1, 3, -4 is a local minimum. Okay. Probably asking where we got the -4 from. You just plug in your critical point in your original function. Okay. So we know f of x, y is equal to x squared plus y squared plus 2x minus 6y plus 6. So that means f of -1, 3 is -1 squared plus 3 squared plus 2 times -1 minus 6 times 3 plus 6 is just equal to -4. So that's where our -4 came in. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. All right, so let's say, for example, we want to find the local extrema for f of x, y is equal to -5x squared plus 4xy minus y squared plus 16x plus 10. All right, so once again, we know to start off, we have to find our first with respect to x, our first with respect to y, our second derivative with partial with respect to x, our second partial with respect to y, and our second partial with respect to x, then y. Okay, so we know that our partial with respect to x will equal -10x plus 4y plus 16, and our partial with respect to y will equal 4x minus 2y. Okay, so this one's a little bit different because, well, not really different, but it looks a little different. We still have to find partial with respect to x equal to 0, and our partial with respect to y equal to 0. Okay, so we have to make this equal to 0. So -10x plus 4y equals -16. Just add 16 to both sides. And we have 4x minus 2y equals 0. Okay, so that would give us x equals 8 and y equals 16. Okay, and we solve that actually using system of linear equations in two variables. Okay, so if you are a little rusty in solving systems of linear equations in two variables, I do have a video posted showing how to do that. You can look in my intermediate algebra folder, and it is there. So if you need a little practice on solving systems of linear equations, the directions are right there, so you can always go back as a little bit of a refresher. Okay, so That means 816 is your critical point. All right, so now we find our second derivative with respect to x and y and xy. Okay, so our second with respect to x, that's going to equal, we find that with respect to x, that's just -10. Our second partial with respect to y, take this one with respect to y again, then that just ends up being -2. Then our partial with respect to x, then y is just our partial with respect to x, and we take that to y. So that just ends up being -10x plus 4y plus 16. We take that with respect to y, which is just 4. Okay, so we have everything we need. Okay, so we know that our d is equal to the second partial with respect to x at our critical point times our second partial with respect to y at our critical point minus our partial with respect to x then y at our critical point. Okay. So we can see there our partial with respect to second partial with respect to x is just -10. Our second partial with respect to y is just -2. There's no variables to replace. Minus our second partial with respect to x then y is just 4. So that's minus 4. So that ends up giving us 20 minus 4, which is 16. So our d is equal to 16, which again is greater than 0. Okay, so just the fact that our d is greater than 0 and our second derivative with respect to x is less than 0, because remember that's just 10. So that means our second condition satisfied, where a, b, and f of a, b is the local maximum. Okay, so we see here that f of 8, 16 is equal to -5 times 8 squared plus 4 times 8 times 16 minus 16 squared plus 16 times 8 plus 10. That means f of 8, 16 is equal to 74. So that means 8, 16, 74 is our local maximum. All right. So once again, if you are still writing, feel free to press pause, but we're going to move on to our next example. Okay. So what if we wanted to find the extrema for h of x, y equals x squared minus y squared minus 2x minus 4y minus 4. Okay, so just like before, we have to find our various first and second derivatives. So we have to find first derivative with respect to x, first derivative with respect to y, second with respect to x, our second with respect to y, and our second with respect to x, then y. So let me clean that up a little bit. That should be y, y. There we go. Okay, so we find our partial with respect to x. That's going to equal 2x minus 2. So we have 2x constant minus 2 constant constant. And our partial with respect to y is going to equal negative 2y minus 4 constant, negative 2y constant minus 4 constant. Okay, so to find out where our partial with respect to x equals 0, we have 2x minus 2 equals 0, so x is equal to 1. Okay, to find out where our partial with respect to y equals 0, is negative 2y minus 4 equals 0, or y equals negative 2. So 1, negative 2 equals our critical point. Okay, so now we find our second derivatives with respect to x, which is 2. Our second derivative with respect to y, this is our first derivative with respect to x, take that to x again. First with respect to y, take that to y again, which is negative 2. And our first with respect to x, then y, remember that's just partial with respect to x, then again with respect to y. So that's going to equal 2x minus 2, and take that with respect to y, which of course is just going to be 0. All right. So we plug all those in. So we have our second with respect to x at 1, negative 2, times our second with respect to y at 1, negative 2, minus our second with respect to x, then y at 1, negative 2, squared. Okay, so we plug all those in. Our second with respect to x is 2. Our second with respect to y is negative 2. See? Trust me, that'll come in. That's pretty important there. And our second with respect to x, then y, at that point is just 0, so it's minus 0 squared. Okay, that's equal to negative 4. So that means that our d is equal to negative 4, and that negative 4 is less than 0. Okay, so that means d is less than 0 means that the point A, B, H of A, B is a saddle point. Okay, so if we find our H of A, B, so H of negative 1, 1, negative 2, almost made it the whole problem without mixing those two up. 1, negative 2. Okay, so that's going to equal 1 squared minus negative 2 squared minus 2 times 1 minus 4 times negative 2 minus 4, which is just negative 1. So that means our 1, negative 2, negative 1 is a saddle point. Okay, so pretty much it's just neither. Okay, so I gave you a minimum, I gave you a maximum, and I gave you a saddle point example. Okay. All right, so let's do a couple more examples to kind of show you some things to expect. Okay, so if you're still writing, feel free to press pause, but we're going to move on. Okay, so what if we wanted to find the extrema for, say, f of x, y is equal to e to the negative x sine of y. Okay, now this one's going to be a little bit tricky, and I'll show you why. Okay, so just like before, we find our first derivative, so partial with respect to x equals negative e, clean that e up a little bit, there we go. Negative e to the negative x sine of y, and our partial with respect to y is equal to e to the negative x cosine of y. All right, yeah, that e still looks a little bit funky. Let me clean that up a little bit more. It's going to bug me if I don't. There we go. Okay. Now, the reason this one's a little bit different, that if you notice that e to the negative x is always positive. For every value of x. Okay. So no matter what we plug in, e to the negative x is going to be positive. Okay. And if you notice one other thing, sine of y and cosine of y are never both 0. For any y value. For any one y value. Okay. So what I mean by that is, let's say, for example, we have sine of pi is equal to 0, while cosine of pi is equal to negative 1. Okay, no value of y will make them both 0 at the same time. They're always going to be 0 for two different y values. Okay, so since we can't have both of them equal 0 at, for the same y value, for this one, there is no critical point. Okay, that's why this one's a little bit different. There is actually no critical point here. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and do our last example. So just hang in there for one more. All right, so let's say, for example, before we found the relative or local extrema. Now we want to find the absolute extrema. So find the absolute extrema of the function f of x, y is equal to 12 minus 3x minus 2y. Now, that's for the triangular region in the xy plane with vertices 2, 0, 0, 1, and 1, 2. All right, so with this, it will probably help you understand it a little bit clearer if I draw like a little bit of a graph. Okay, it doesn't have to be completely precise, but I just want to draw my XY graph first. Okay, so this is our X and this is our Y. Okay, so let's say you have the point 0, 1. Let's say you have the point 1, 2. And let's say you have the point 2, 0. That's how the triangle would look. Okay. Now, the quickest mistake a lot of people would make, and I don't want you to make it, that's why I'm telling you about it, is say, well, that's obviously the maximum and this is the minimum. Not really, because what this really is just another way to write this. X, Y, Z. Okay, so what if this is our X is 0, Y is 1, so this is our 0, 1. Okay, this is our 2, 0. And this is our 1, 2. Okay, so there, and this one's there. Okay, so this is really just this. So this looks like this in 3 dimensions. Okay, so somewhere above this, this is our region. Which means whatever shape is hovering above, we don't care about the whole thing. We just care about the shape just above this triangle. So if this goes up, whatever shape is up here, we're just cutting out a little bit of a triangle, and we want to know the highest point and the lowest point inside that region only. Okay, hopefully that kind of clears up this problem. I know looking at it can kind of jump off as a little confusing. Okay, so sometimes you have the XY plane where it's X between X equals Y and Y equals X squared or something like that. So you draw both of those in 2 dimensions, flip it over in 3 dimensions, and you want to find it over that particular region. So the regions can change up. Just so happens this particular region is a triangle. All right, so we're going to go ahead and solve this. Okay, so the first thing you'd want to do is you want to create an equation for each one of those lines, so you can find the minimum and maximum value for each one of those lines. Okay? So create an equation, y equals mx plus b, for each line, or each line segment. Make sure, there we go, you have enough room. So each line segment. Okay, so what if we have to go from the point 0, 1 to 1, 2? Okay, so if we figure out the slope, we know that the slope is equal to 1. So we know it's y equal x, but we have to find our y-intercept, where when x is equal to 0, y is equal to 1, and that's just x plus 1. Same thing here, when x is equal to 1, y is equal to 2, so you know you're right there. So that's where, you know, for y equal between here and here, that x goes between 0 and 1. Okay. So what if we have the point from 2, 0 to 1, 2. 2, 0 to 1, 2. Or 1, 2 to 2, 0, doesn't matter which direction you go. Because either way, you're going to end up with a slope of -2. And when x is equal to -2, you want y to equal to 0. So if you plug in, well, x is equal to 2, then y is equal to 0. So if you plug in +2 for x, you end up with -4. So that means your y-intercept will have to be +4 for that to equal 0. And same thing here, you can always double check with your other point. You plug in 1, and your y is equal to 2. And that's where your x is between 1 and 2. Uh-oh, about to write 0. Okay, so now you think of your third line, which is between 0, 1 to 2, 0. Okay, so we're doing each individual line. Okay, so you already know your slope. You figure out your slope, that's going to be -1/2. Okay, so when x is equal to 2, you can always use the 0 if you wanted to. Then y is equal to 1. That'll be +1. Same thing here. When x is equal to 2, y is equal to 0. So you know that's right. And that's where your x is between 0 and 2. Okay, so we have our three equations. All right. Now, if you remember, your original equation, f of xy, is equal to 12 minus 3x minus 2y. We're going to replace that y with each one of those equations and then find out the minimum and maximum value using our interval here. Okay, so when, let me move that up a little bit. Once I get to writing, I might forget. Let me kind of separate that a little. So when y is equal to x plus 1, that means our f of x, y, just becomes a function of x. Because we replace that y, and we end up with 12 minus 3x minus 2 times x plus 1. So if we distribute that -2 and combine like terms, we end up with -5x plus 10. Okay. Now, if you look at x between 0 and 1, the max is equal to 10. And the minimum value is equal to 5. Okay, so if you plug in x equals 0, you get 10. If you plug in x equals 1, you get +5. Move that up a little bit. Okay. Now we do the same thing for y equals -2x plus 4. So, -2x plus 4. Again, our f of xy becomes a function of x because we're replacing the y. Okay, so that's 12 minus 3x minus 2 times -2x plus 4. Okay, so if you distribute and plug everything in and combine like terms and all that good stuff, you end up with x plus 4. Okay, now between x equals 1 and x equals 2, we see the max value that we have is equal to 6, and the minimum value we have is equal to 5. Okay, so last but not least, we have our y equals -1/2x plus 1. So when y equals negative 1/2 x plus 1, again, our f of x, y, becomes a function of x. We have 12 minus 3x minus 2 times negative 1/2 x plus 1. Again, once we distribute and combine like terms and all that good stuff, we end up with negative 2x plus 10. Okay, now between 0 and 2, 0, 2, the max value, okay, that's going to equal 10. And the minimum value is going to equal 6. Again, just plug in your 0 and your 2. You get your minimum and maximum values. Okay, so that means your absolute maximum value, you look at all your values here, you have a max here of 10, a max of 6, and a max of 10. So your absolute maximum value will equal 10. And your absolute minimum value, okay, you see here your absolute minimum is 5, 5, and 6. So your absolute minimum will equal 5. That's the smallest out of all three of them. Okay, and you can pick which one. You can say your maximum at 10 is at 0, 1. And your maximum at 5 is at 1, 2. Okay, your minimum max just can't be at the same point or on the same line. Well, it could be, but when at all possible, make them on different points. All right, and that is equal there. Okay, so that's how you would find the absolute minimum and maximum. Again, remember, your region doesn't always have to be vertices. It could be, like I said, between y equals x and y equals x squared. It could be between the y-axis and x equals 4. It could be a various group of combinations. Okay, this is just one combination to show you how to kind of approach it. All right, so hopefully this made sense, and I will see you on the next video.